All right, before I start writing tests for the linked list implementation, let's just update the test.go that we had here earlier so that we're using our new linked list rather than using the quick and dirty one we wrote earlier. And if we did everything correctly, we should just need to use the right type and things will just work. Maybe some modification because we kind of changed the signatures for the get here and stuff, right? All right, so what do we do here? So I'm going to declare the list in a more explicit way because I want to use the interface type as its type, right? And so we do data structures linked list. So this is the interface linked list, right? Whereas when you come here, instead of using this circly doubly linked list that we defined here, let's go to linked list and use the create method here, right? Now this returns linked list that's defined in this package, but it should be compatible with this data structures linked list, and that we kind of just test that by default there, right? Oh, and then since it's more explicit, we don't use this kind of the type inference assignment operator, and instead we just use the normal one because we're being very explicit here, right? And as expected, these throw errors because get signature now has a from back, right? So we're just going to do false because the get that we defined earlier didn't have a from back. It was always from the front. So we'll just kind of sub that in. Now everything else compiles. That's awesome. So just to get a quick sanity check, let's go ahead, come out here. All right, where am I? Let's go to Go, and then we're going to go into local, source, local, not data structures, but rather test. All right, and then we can do our infamous go build, and it should just be test now. Boom. All right, so an initial size should be 0, it's 0. Final size should be 3, it's 3. We get harsh here, we get something here, 999 here. So everything works. That's awesome, and that's exactly what we expected. We can further prove that we have completely now using the other stuff by deleting all this quick and dirty implementation we had here, right? So node goes away, circly doubly linked list goes away, all its little methods go away. We'll leave person behind because we're still using that. That's just part of test code here. And then we'll go ahead and run this one more time, and things still work. I love it. Okay, so that's our quick and dirty sanity check, right? And that worked out. So before we move on to writing unit tests, I'm going to do something weird first. So I'm going to implement my own assertions. Now don't do this. You can do this as part of this exercise with me, but don't do this in your production code for sure. The testing framework built into Go, which we'll see here in a second, is very feature-rich and covers all these assertions that I'm going to implement, and then a bunch more. I do the custom assertion implementation stuff as an exercise for myself, and I've done it in a lot of different languages already. I've implemented similar assertions just to play around and get an idea of things. Back in the day in Java when I was getting more comfortable with it, Perl, Python, JavaScript, all the little flavors of JavaScript that exist now, like TypeScript, Flow. I've even done it in Bash. And that's something I just do to, get a better muscle memory in a language, essentially, and get a better feel for it. But for production code, definitely use the official stuff. So just that quick disclaimer there, right? Having said that, I'm going to create a new top-level directory here. So let's create a new folder. Let's call this guy test utils, because I'm going to put in some test utils here. And under in here, we'll create a new file, and I will call it just testutils.go. I'm not going to have much in here. Right? So we'll keep the package name the same. I am going to import, and I like the parentheses here, but since we're going to only import one thing, this is the official Go testing package, and its utilities. And we're going to only use it for a very narrow purpose, to declare errors, because I don't want to reinvent Go's way of failing a test, right? So we'll continue to use that, and then essentially I'll go ahead and implement 4 assertions that I think are pretty basic, and I can essentially use those to write the vast majority of unit tests. Occasionally I'll need a mocking framework, but really my philosophy to unit testing is keep it simple. KISS, or keep it simple stupid, is a very fundamental design principle. It's really all of engineering. For unit testing, to me, it means I can test pretty much any code I ever write with the simple assertions I'm about to implement right here. Right? Occasionally, I'll need a marking framework, as I said, but especially when testing code that depends on databases or protocols like HTTP, yeah, I'll need a marking framework. But here, you'll see me reach very high levels of code coverage with just these simple assertions. And plus, they're kind of fun to write, so, I just write them. All right, so let me go ahead and write the skeletons out, and then we'll implement them. They're not that hard to implement. Okay, so these are the 4 assertions I've been talking about: assert true, assert false, assert equals, and assert panic. Okay, so assert true and assert false are fairly straightforward. Really, you just need one of them, but having both kind of keeps things convenient. And they're fairly straightforward. So first I'll just go ahead and implement assert true, and you'll see how assert false can just be implemented using assert true, right? So it's fairly simple. We pass in some condition, and if that condition is not true, if it's false, then we use, and this is where I was mentioning I'm going to use Go's testing package to really throw the errors, because that's a little too fundamental for the reinvent here. And then we'll have the the user of this package, this testutils package, pass in whatever error message they want to show. So it's kind of friendly, right? Cool. So we throw out that message, and that's really it. And then for assert false, we just basically say, hey, assert true, and then we pass in the message as is. We just flip the condition, and then we pass t as is, right? Perfect. All right. What's next? So assert equals, you'll notice that in the comments I've mentioned, hey, the assertion is done using this inequality operator. And it's important to spell that out, because I'm not going to be using this to assert equality on your literal structs, maps, and slices. This is going to be really reserved for strings, number types, and pointers. The actual memory address is held by pointers. So if this pointer 1 and pointer 2 both point to the same memory address, they're equal. That can be asserted through here, but not that this literal struct and this literal struct are equal. That Go doesn't really have a quick way to do that. You pretty much have to either use reflect, which is kind of a third-party package, or write your own function. I plan to just kind of write my own function where I do my own deep copy by asserting equals on a struct's fields as I see fit. Or come up with some other clever way to say, hey, given this condition, I know what I'm looking for is actually true, kind of thing, right? All right, so with that caveat out of the way, we'll say if expected does not equal actual, then go ahead. And here, instead of using t.error, I'll use error_f, which is kind of like fmt.printf that we've been using, where you can actually have substitution variables, right? So basically we do %v. Cool. And so you can see basically that we're using %v as the value substitution here. So message expected actual is just basically in that row. So first we print out the message, then we print out the expected, and then the actual, right? We just want to have more detail here, given that it's actually an equality check on 2 things. So this is actually the fun one, the assert panic. So this kind of asserts that a panic occurred before this function call, right? And relies on Go's defer and recover. You don't see defer here. Defer is used to call this function in the function where we're asserting the panic. So basically, Go makes use of the call stack with this, right? So if you defer some code, and you kind of do that by saying defer, some function. If you write this, and this is not actual code here that I'm going to put in assert panic, this is for example. So if you write this code, what happens is Go takes this function, or whatever arbitrary code you have here, and puts it basically right after the function being executed on the call stack. So it's kind of like the opposite of calling a function from a function. Like if you just did some function, the language will basically put this on top of the stack, start executing it, so that when it's done executing, we'll go back to here, right? So with defer, basically, you do the opposite, and the function call then goes behind what's currently executing. And it's typically done to guarantee cleanup stuff, like shutting down expensive objects, freeing thread synchronization locks. So you can basically think finally in Java, right? You want to just make sure some piece of code definitely execute at the end of that method every time, right? And that's where you usually use defer. Here we're using defer to assert panic by using recover. So let me write that code. And so the way we're going to write it, and it's going to be a fun way, I'm going to write the if here as well, where basically we define a variable just so we can use it in this if condition block here. And here basically I'm saying I'm going to recover, and recover should basically return any panic that happened while the function that was executing before, basically the function that deferred this guy, was executing. So if I don't have something returned, that means a panic didn't happen, and that's when I fail, right? And that's when I print the message that's been sent to me. Okay, so given that, and if this is confusing, this will make sense, crystal clear sense in a second here when we start actually using it in our tests. But given these 4 functions, now we're ready to start actually writing unit tests. So let's do that. All right. So as far as unit tests go, typical convention in Go community is to write your test code in the same directory as the code under test. What this also does is it allows your unit test to be in the same package as the code under test, so it can have access to internal fields, functions, and types. And unit tests should be pretty white box in nature. So if you're familiar with testing types, there's white box tests, black box tests, green box tests, right? So black box tests are typically what a QA would run. They should definitely be testing just the external interfaces and very much the publicly exposed parts of the system, right? And really exercise the system through those interfaces and make sure it behaves properly. Unit tests are white box, meaning they just go right into the guts and they manipulate things as much as possible. Now, you do have to exercise discipline, making sure you do at least stay at the function level. So you're testing one specific function and you're calling it the way the function is called in production code. But you're completely allowed to, take a class and mock out its internal state and things like that, or call a private method, all that stuff. So unit tests are white box tests, and so having your unit test have access to all that internal data that they can manipulate and kind of examine is completely fine, right? So that's cool. So let's go ahead and do that. We'll go ahead and create a new file here, right? And we'll call it linked list, and you can just come with a naming convention. I am using this wherever I'm doing an underscore, wherever I'm doing a test file, I'm doing an underscore test, so that it's kind of different than the dash. Doesn't mean to follow that. It's something I've invented. I don't know if everybody else is doing it or not. All right. And then I'm not gonna sit here and make you watch me type every line. So let me just magically write out all the test code up front, and we'll quickly go through it. All right. And boom. All right, so let's go through these things. You'll already see seeing testing and kind of these test blah, and really I think it's a testing package being in here is already telling Go that these are tests, right? I'm not 100% sure what tells Go, but I think it's either the combination of having this underscores test or having that testing package being imported or having tests in front of the names. One of these things is triggering it, and I'll have to go look it up. But it's very obvious to Go based on something we did that this is a test file, and this run test comes up for VS Code, right? Okay, so right off the bat, let's look at some of the key ones. So for test create, we make sure that the list is empty, and that some of the methods that initially return sensible stuff based on that state, right? So we create the list using the standard create method. And then we basically, check size and say, hey, it is actually 0. We create an iterator on this empty list and do call has next, and that better return false, right? So we sort of false on that. Cool. This is another key test that I like, which is test satisfies linked list interface, right? So I've created this test. So right now, obviously, we just coded all this, so it definitely satisfies the linked list interface that's defined in the base package. But that might not be the case as the code evolves and multiple hands starts touching it. So this guy will exist to make sure the compatibility stays. Now, if you're in Java world or other more strongly and really more explicit languages, you would need this test. It would just be part of syntax, right? In Go, it's not. So to keep that sanity in place, I'll go ahead and write a test for that because this is very important for my module, right? Okay. Most of the rest of this stuff is now testing all public methods and putting them through various logic paths. So I have all this code in GitHub as well, and the link will be in the text part of my blog as well as the YouTube video description. So feel free to go review the finer details more elaborately at your own pace. I'll just kind of scroll through the stuff. As you can see, I'm testing each method at a time. Iterators, I basically test them out in one method each for each one. Whereas insert and some of the other ones, clears, gets, all those guys, I have different cases captured in specific methods, right? So feel free to go through this stuff, see exactly what's going on. You'll see a lot of invocations of the method, the assertions we just defined earlier. Cool. Next, what I really wanted to cover was showing you the usage of assert panic. Awesome. So here is one right here, and there's a few more down below. So as you can see, we defer the panic assertion before we actually call the specific code that will in fact lead to a panic, right? So this is a list of 2 elements, and we're doing a get with an offset of 2, which is going to be 0 based, right? So we're really looking for the third element. It does not exist because we only put 2 things in the list, right? So this code is going to lead to us dereferencing a nil pointer, which will cause a panic. So before we go into that code, which we expect to cause a panic, we basically defer it. We defer the assert panic check. And this passes right now because, so we just run the test and it passes because I know a panic is going to happen and I assert for it. So just to prove that this does work, let's do get 1, right? Because that should not panic. That should just get back this 2. So let's go run that, and that then fails. And why does it fail? Because we expected out of bounds get to cause panic, which is the message that I put out here. So this is how it kind of works. We defer it. So this doesn't execute right away. It gets put on the call stack right after this guy. So this needs to still finish executing. This guy gets executed. It throws a panic before Go panics all the way out to crash into a program. It actually calls this method now. So we go back to our test utils. So we start executing here. We call recover. This guy returns whatever the panic was. So when we had a 2 in there, there was an actual panic. R did not equal nil, so we did not enter here, and the test is passed. Now that we changed it to 1, so there was no panic, so this did return nil. So this became true, and we had an error. So that's kind of, that's how that works, essentially, the test utils are a panic there. So, and that's it. Okay, so now that we have written all these tests, the next thing we want to do is actually run them from the command line, right? So for that, we just basically run go test. I'm in the same directory as, where all the code is, essentially, where the test file is. So I can just basically run go test here, right? So I do that, and I pass. That's awesome. Okay. So next, we want to make sure we're actually testing what we want to test, right? So we can just write whatever we want to. We could have just written tests that don't do anything, and they pass. Who cares, right? They're not doing any actual work or anything meaningful. So the best metric, in my opinion, in the unit testing world is unit test coverage. Just figure out what lines actually got executed during your test, what branches got covered, all that stuff. So cool thing about Go, which kind of doesn't exist in some of the other language communities, a lot of that stuff is built into just the standard Go install. I love it. In Java, JavaScript, all these other places, you get into just unit testing, framework hell. Not hell, but you basically have to rely on third-party tools to get that information. It's not really built into the language. In Go, it's all built into the language. It's awesome. So let's go ahead and run a coverage report as you run the test, right? So there you just basically pass in a argument to your Go test, and that is Go cover profile. And this argument basically takes a file name, and so we'll say coverage.out, right? And then we'll go ahead and run this test. It says I have 100% of my statements pass, and if I do an ls here, you'll see that a coverage.out file got created in addition to all these other guys, right? And that's awesome. So now how do we read this coverage.out? So my preference is to view it as an HTML file. So that's what I've been working on. So we'll use go tool cover, and then we'll pass in the HTML option to it. And then we basically pass in the file at the end. And that essentially, and you don't see it right now because I have multiple monitors, so I'll bring in the report that just popped up in my default browser, which is happens to be Chrome, right here. And as you can see, this is the coverage report, and it's all green because I have 100% coverage. Now, a coverage report when you have 100% coverage is not that great because you know everything's already covered. Where it does come into play is when you have less than 100% coverage or less than ideal coverage, and you want to go figure out, well, what lines specifically you're not executing, and then you would see them as red here. But it basically shows you all the non-test, basically production code files, and you can see what's covered, what's not covered. Here I wrote pretty exhaustive tests, so everything is covered, so that's great. So that's testing. So now I'm just going to go on and move to the next thing. And again, I went through testing pretty fast because I don't see a lot of value in you watching me type every single line of test code, just to get the fundamental concepts across. But feel free if you've been using this to kind of write code with me or something like that. Just go to the GitHub page, and then look at the code and go at as slow of a pace as you want to. But now that we've come this far, let's go into the next thing. Let's go ahead and implement queues and stacks now using our linked list implementation. Boom. Okay, so I'll focus on queues first. With the circular doubly linked list implementation we have thrown in here, implementing a queue is going to be stupid easy. As a refresher as to what a queue means conceptually, queues as data structures model a simple queue from real life. So we are all used to them. Anytime you're at a grocery store, at a bank, in the airport security line, you're in a queue, right? The first person who got there gets to go first, and they're going to be the first to get to the service. And the last person is going to be last. And then that concept is FIFO, right? First in, first out. So that's basically what we're going to implement here. And so with that in mind, with queue you typically have two main operations, right? You have queue and dequeue. So let's go ahead and I'll go ahead and create this file, queue.go, and it's going to live in package queue. Great. Okay, and as I said earlier, two main operations, right? Queue and dequeue. And what are they? Well, queue adds new element to tail of queue, right? Whereas dequeue removes and returns the top of queue. So in, out, right? I'm going to add two other convenience methods. Well, not really convenience, but kind of, something that kind of enrich the functionality of this abstraction. I'm going to go ahead and add a peek. And peek is the same as dequeue, except it's a trial run. It's a dry run, right? It's not going to remove, it's only going to return the top of the queue. So with peek at the top of the queue, you're not really committed to dequeuing the element that's up next in the queue yet, right? You just want to get a taste of what it is. And I'll also add a size, which will return. So size returns number of elements currently in queue, and this is just a standard operation. We've done this for linked list already. In fact, we're going to just leverage that implementation, because as far as state goes, we just need to hang on to a single linked list internally that the queue will delegate all the real work to, right? So speaking of that, we're going to say queue implements, and I want to do this as a comment, sorry. Queue implements standard FIFO queue, right? And I'm not going to get into explaining that in too much detail in the comment because queue is a pretty standard concept at this point in computer programming, right? And the only thing I want to hang on to here is a doubly linked list, which will grab. As you'll notice, I'm using the interface here. I'm not going to look at the actual implementation type. I want to code to my interfaces because that's more than enough as far as what I need to refer to. However, I am gonna follow suit with the constructor pattern we've established before, and I'm gonna put in a create method here, right? And here we won't do zero value initialization. will actually create a linked list, which will be empty as well, but it won't be nil as far as Q is concerned. And here, we'll go ahead and actually refer to the implementation, because you can't really instantiate this. This is just an interface. We need something real when we're actually instantiating stuff, right? All right. And so here, return a Q. But here we need to actually instantiate it, and we refer to the linked list instead. And that should be all happy. Awesome. And you'll notice my editor is doing all my imports automatically as I'm typing. That's what a good IDE does, right? Writes all the boilerplate crap for you. Boilerplate crap for you. Okay. Let's go ahead and start implementing. The rest of the methods kind of write themselves after we've done all of this. And this is really an exercise in how modularity and reuse looks in Golang. We did all the hard work here, and now the fruits are paying off. We can just easily write this out. We refer to things at the highest level possible. We bring in a data structure linked list as an interface. We use its operations. We don't go into the guts of this thing because we are a different package, right? So we only deal with publicly exposed types and methods, sticking to the highest possible abstractions possible, including to interfaces. And we go ahead and pound this out. All right. So let's implement Q. This is interesting. This shouldn't have happened. Okay. And I'm just going to leverage the add method, which will add things to the tail of the list, right? Which is what we want. We want things to go to the end. Awesome. Great. So peak returns the value that you have been putting, right? And here I'm going to put a nice little guard. I'm going to actually refer to a size method that we haven't implemented yet. So let's go ahead and implement that real quickly. And as you can tell, I'm basically just referring to the methods on the doubly linked list as much as possible. All right, let's see what the issue is here. I think that's really affected by what's going on up here. So let's go ahead and finish this implementation out. Boom. All right. And then finally, we'll go ahead and implement DQ, which will do the exact same thing. So what I'm going to do is actually want to copy this because the contract looks pretty much the same, except the mean's different. And we, instead of doing a get, we'll do a delete because we're going to delete things from the list. Awesome. So with that, we have a pretty functional queue working here. And how do we prove that it works? We're going to write some unit tests. So let's do that. Okay, so unlike the last test, I'll go ahead and write this one out with you guys, kind of do the whole thing live, because it's shorter and it'll be good to go through a test file together, right? So just like last time, we'll do q_test.go. This underscore test is important. I realized why I had started doing that as a Go convention, and it tells Go this is where the tests are at, right? So the moment I do that, of course, it's going to be in the package. And you can see this run package test, run file test thing comes up all of a sudden because the file name has underscore test. That's a convention for Go to know that this is where the tests are. And VS Code's Go plugin, kind of recognize and pick that up as well. Okay, so I'm going to create a test type here as well, and we'll call it student. And we'll use the instance of students as elements for our queue as we test it throughout this file, right? So, and it's going to be a struct, obviously. And then a student, we'll just put the most basic stuff we can think of, right? Student has a name, student has a grade. Awesome. So in here, I'm going to go ahead and only test create, peak, and DQ, right? So the way we do that is basically func test create, right? And we'll pass it testing. So I'm testing dot t. And I'll just go ahead and copy this twice. And we're testing peak as well as DQ. Yeah, right. Okay. So we can actually run the test right now, and everything will pass, right? Everything passes. But we're not testing anything, and that's why I like relying on coverage, right? Because if we go ahead and run our cover profile, we'll just create coverage.out again. And then basically run that. I'll again bring in the generated file in here, and you can see nothing is covered, 0% test coverage. So our job is to make sure all of this goes green, right? All right, so let's kill that for now. And we'll come back and we'll start with test and create. So create is straightforward. Basically things are 0 or nil all the way. So yeah, essentially 0 values, right? So we'll go ahead and create queue. And here I'll refer to the create method. And that resolves because there's only one create method in this package. We have a linked list.create that's different, and I would have to do linked list dot to refer to that, right? Okay, so we create the queue, and then I'll use my assertions that I created earlier to go ahead and assert that things are 0 or nil that are supposed to be. So what state can we look at here? So we can definitely look at size, and queue size should be 0. We can try peeking onto the queue, and we shouldn't see anything. There should be nil there. And we can try dequeuing from the queue, and that should also return nil. And this the philosophy here is a little different than in the linked list. In linked list, if you try to get the 0th element or whatever element, whatever offset while the list is empty, it would throw panics at you, right? It's like, hey, you don't know what you're doing, and I want to throw up on you for it. Because the linked list, I want it to be a bit more of an advanced thing for the caller. The caller has to be kind of aware of what they're doing. Queue have been made to be very easy to use and very kind of dumb because it's a convenient abstraction. There's no reason to make a convenient abstraction be inconvenient, right? So I'm going to keep convenience in mind here, and things are going to be nice. Nothing's going to just break on you as long as you keep using publicly exposed methods. And things will return something sensible back. So here we'll return 0, we'll return nil instead of throwing a panic, right? So let's expect size to be 0. And I have to cast it to uint64 because if you leave the 0 naked here without the cast, then Go treats it as an int type, which would be incompatible with what size here returns, which is a uint64. So we want to make sure we keep our size compatible. I'll copy this so I can type less. So in addition to size, we also want to look at peak, and we want it to be nil. And we also want to look at DQ, right? And we want that to also be nil. So this becomes nil. This becomes nil. Peak as well as DQ. Great. So this I should be able to run. And things still pass. Great. I'll go ahead and create a new coverage.out, right? And now, if I come through here, you can see I've got some green. I've got about 2/3 coverage, right? 66.7. So the stuff I'm missing is we haven't really tested peak or DQ, and because we haven't tested those things, we haven't really put anything in the queue yet because we hadn't needed to, and so we haven't really hit Q yet either. So all right, so let's go ahead and test the rest of the stuff. So let's test peak, and this time we'll actually queue some things, right? And I'll use me, my brother, and my cousin as our test students. So just in that order, I'll go through things. So we'll go ahead and create, sort of a queue again. Before we do that, I'll go ahead and create some students. So we'll have me, we'll have my brother, and we'll have my cousin. And there'll all be pointers to a student instance, right? So it's me. And let's say I'm a smart guy, and I got an A. And let me go ahead and copy this so I can just kind of modify this one more time. Let's say my brother, not so smart, and he is kind of struggling with a C, but passing, so not the worst. And let's say my cousin is better than all of us. She's the best, and she's got a perfect score, 100. Awesome. Pretty typical. All right. With that, let's go ahead and create my queue. And again, for each test, I'm creating a new queue. So anything I did here is just completely gone because I've got brand new things to work with here. And that's a pretty decent thing to do as far as setup for your tests. Keep the data and all the setup and cleanup as contained within the test as much as possible, right? Okay. So I'll go ahead and queue myself. My brother next. And my cousin last. Okay. So in this one, we're going to go ahead and test peak, right? So basically when I call peak, I should get the first thing I put in there back. And no matter how many times I call it, it should still be whatever was there first. So let's go ahead and test that. So once again, I'm going to use my assert equals here, right? And I expected Saharsh, right? Great. Sorry, not 0. Size here now will be 3. I need to go ahead and close my quotes there. All right, so let's run this test. And that passes. That's awesome. That's exactly what we expected, and that's what we got. So what I'm going to do is actually do this 2 more times. And let's go ahead and run this one more time. Boom. All right. And with that, I can go ahead, update my coverage, and see where we're at. And now, you can see the only thing missing is DQ because we haven't really tested that yet, except for the MTQ case, right? Cool. So we're doing pretty good, almost at 90% coverage now. And with the last test, we'll try to knock that out here as well. All right. So finally, we get to DQ. We'll do the exact same exercise we do with peak, but see that every time we DQ, the queue actually loses its top element, and it'll keep doing that until we get to nothing, right? So to get set up, I'll go ahead and at least copy this much. I'm copying too much because I've already got the signature there. Great. All right. So how do we modify the test? I'm going to leave the setup alone, right? And I'm even going to leave this alone because I do expect 3. And then on my second one, let's go ahead and DQ in fact, right? So you can copy this probably. Just modify it. So the first time we DQ, we should see we should see Saharsh, right? All right. So let's do DQ here. Great. Now when we peek here, though, we should get back to the second element, which is now Sean. And we should see Sean here. Awesome. And now our size should now go down to 2, right? Because we have DQ. Great. I'm going to go ahead and make this the last case, where on the last DQ, we should see nil, right? And expect my size to be 0, no matter if when you want to start DQing. Before we get there, though, we have 2 more cases to capture, right? So next time we DQ here, we should choose Sean. And after Sean has been DQ'd when we peek, we should now see Nano at the top of the queue. And our size should go back to 1. Awesome. Alright, and then finally, on our final DQ, with actual value coming back, we should expect to see Nano on the DQ, right? And on the final, on the peak after that final DQ there, we should see nil, right? And our size of the queue should now have gone down to 0. So we're basically DQing until we get to nothing, right? We empty out the queue essentially here. Awesome. And let's run this test. And it fails. And I'm pretty sure this is because I did something stupid so far. So this happened at 20. So we expected nil. Expected Nana saying 100. So here is where my problem is. I didn't go ahead and change this. Okay. So my test was written badly. And let's try that one more time. And now things actually pass. Awesome. So we expect Saharsh up front, size to be 3. When we DQ, we get that Saharsh that we peeked at here. Next time we peek, we see Sean peeking back at us. And our size is dropped to 2 because now only Sean and Nana are in the queue. Saharsh has gotten out. Next time we DQ, we see this Sean that was peeking back at us here. And then now Nana's up top, and size has gone down to 1 now that Nana is the only one in the queue. On the final DQ, we get Nana out, and then Q becomes empty. And then we can keep calling DQ after that, but we get to that empty queue state, and we just keep getting back to 0 size, right? Awesome. And that works. And then finally, I'll go ahead and run my coverage one last time, and now we are at a good 100%. Awesome. So stacks are next, but before I move on to that, I'm getting a little tired of doing this 2-command thing here to get the coverage report, and the coverage report is local to the package I happen to be in and all that stuff. So I'm going to change that so I can make things a bit more efficient. So I'm going to go ahead and create a bash script that runs my go test coverage and all that stuff for everything in one go. That is a subdirectory of this local folder here. So let me do that. I'm going to call this script test all, right? So I'll create a test all.sh. And I'm going to go ahead and implement a bash script. I'm not going to make you guys sit through every single line. So instead, let me just write this whole out, and I'll meet back with you in a sec. Okay, so here's my test all script. And basically, in this guy, I'll go ahead and run go test from the script that this guy is in. So basically the top level directory here. And I'm going to have the option to show HTML if on an optional basis, right? So only if you want to have the list of the coverage report as an HTML file pop up, then we'll go ahead and run coverage. Otherwise, we'll go ahead and just print out a number, right? So I'll do that. So let's go ahead, and I don't need to be in that directory to actually run it. So from here, I actually need to go ahead and give execute permissions. Cool. And that runs everything, and it gives me 100% coverage for linked list, 100% coverage for queue. I didn't put any things in test or test utils, no test files there, so it doesn't run anything. Data structures just has that base.go. So, it's only interfaces, only type information, so nothing really test there, so there's no test there either. This doesn't have any test because it's a driver thing, right? And then I can run my show HTML flag in there. I'll actually go and generate my HTML report. And boom, and that gives me essentially here everything that I've done so far, right? So all the classes here in one go, and a global coverage percentage number. So I like it. So I'll start to use that, so we don't have to keep running, the report individually for each package here. And I'll go back out, so that I'm at the local spot. Okay, I can go one more level up, so that I'm in the Go directory. And then let's move on to stacks. Stacks are opposite of queues in that they follow the LIFO order instead of the FIFO order. And LIFO is, LIFO, which is last in, first out. And you can kind of see that as modeled after, if you think of just any kind of a stack in real life or in the physical world, when you create stacks of papers, right? You have a bunch of loose sheets of paper that you're trying to collect and put into one organized stack. You're going to put each sheet on top of the other. And the first sheet that will be accessible to you will be whatever's on the top of the stack. So the last sheet of paper that you put into the stack is the first one you're going to get out. And that's the concept with stacks, as opposed to queues where it was, first in, first out. And stacks are pretty handy. They come, a lot of implementations and different things of software do well by leveraging stacks. But I won't get into that here. Feel free to go read the Wikipedia on it or a good programming textbook, and they'll cover that in detail, CS 101 stuff, right? But instead, here we'll just quickly implement our stack with the circular doubly linked list that's already in place. And again, the driver here is showcasing how modularity, reuse, all that stuff works out in Go. And in fact, the stack implementation is so similar to queue. I'll actually start with just copying the queue implementation we've already coded up, copying that to the stack folder. We'll go ahead and rename this guy to be stack.go. I'll come in here, I'll do a case sensitive, and it is case sensitive here. Find and replace, where we take queue and replace it with stack. Okay, and so that goes away, that goes away, that goes away. I'll go ahead and skip that one, because we'll rename that to something else in a second here. As well. Great. And then we'll also go ahead, I'm going to go ahead and get rid of that. I'll go ahead and rename this guy by using the rename symbol. And we'll call him stack. Great. Except that didn't do anything. Okay, much better. Great. So we've got a good starting point. I'm not done with the implementation quite yet, because instead of queue and dequeue, in stack we have push and pop. So while queue in the queue implementation adds new elements to the tail of the queue, here we're going to call this guy push instead, which is going to push new elements into the stack. But instead of going to the tail, it's actually going to go to the head of the stack. We're not going to change the implementation here. It's the internal list that we're maintaining. We're still going to put things to the tail of that list, but we'll treat it as the head of the stack. And we do that by coming here, and we can change the peak. We can keep the name same. We can still peek at the head of the stack, peek the top of the stack. But top of the stack is not going to be the head of the list anymore, the head of the internal list. Instead, it's going to be the tail of that internal list, right? So basically, as we add things to the tail, we have A, B, C, D, E. So as you're adding things, you're still on the tail of the list. But if you treat that as the head of the stack, you'll get that last in, first out order, right? So leveraging that, we've got our stack implementation in place. And obviously we want to do the same thing here in DQ, except we're not going to call this DQ anymore. Instead, we're going to call this push. Sorry, not push. Pop. So pop removes and returns the top of the stack, right? And everything else looks the same, except instead of going to the head of the list, we're going to the tail of the list, similar to how we were doing in the peak. And we should be good to go. I'm going to give it one more look over. So stack implements a standard FIFO stack. Oh, it doesn't. It's a LIFO stack, right? So that's a good catch. Internally, it's still a doubly linked list that we're trying to leverage for all these implementations. We are creating an empty stack here. That's great. Push adds new elements to the head of the stack. That's great. The implementation is the same as Q's Q method. Peak, we have switched over the implementation. Otherwise, it looks to be the same. It's still the top of the stack that we're grabbing things from. And pop, similar to peak, goes to the tail of the list, so it can return the top of the stack. Awesome. Size is still the same. Great. So I think that was it, and that was a pretty simple implementation, as you can probably see, especially after having implemented Q. And now we're going to go test this thing. Let's do it. So I've gone ahead and implemented the tests for stack, so that you don't have to watch me type it all up. They're very similar to the Q ones, with just minor changes, kind of like how we minor change the implementation. And just like before, we're going to test create, peak, and then instead of DQ, test pop. And as a virtue of that, size and push get tested, right? So you'll notice that the structure is very much similar. Create is pretty much identical, right? You just create something and it's empty. We just proved that. Peak is where one of the changes happens. We still insert things in the same way we did with the Q test, except you'll see now that the head of the stack is going to be Nana instead of Saharsh because it's last and first out, right? And that becomes even more obvious here when we do start popping things. Still the same insertion order, but then as we pop, it's Nana first, then Sean, then Saharsh. We're going opposite order. But otherwise, things are very similar to the Q test. I'll run package test here, which is still just run this guy. Great. And here I'll go ahead and run test all sh with show HTML. This will run everything in my local directory here. And let's do that. Oh, obviously that command doesn't work. Instead, what I need is source local test all. That works, and then I just want to do the show HTML. And you can see it's 100% coverage in stack now, in addition to all those things as well. And we can just see the green here with the HTML report as well. Awesome, we're good to go. And on to the next thing.